Hello, my name is Deborah Oga, a master's degree student of the Wireless Network and Future Internet Research Unit in the Electrical Department under the supervision of Associate Professor Dr. Chaudit Aswako. This is the presentation of my research work titled Assessment of Greenhouse Gas Emission Reduction Potential through Transmission from Gasoline Power to Electric Motorcycle by using Sumo, Preliminary Case Study of Saturn Area in Bangkok. This is the outline of my presentation. Among the many sectors that contribute to the release of greenhouse gas emission, the transport industry happens to be one of the major global contributors. In Thailand, there is about 22.6 million motorcycles, which is more than the entire vehicle fleet in the country. The chart shows the introduction of new motorcycles and cars into the country from the year 1991 to 2023, and we can clearly see that the number of motorcycles is much more than the number of cars. This is because in most developing countries, motorcycles are relatively affordable than cars. They have lower taxi fares and are more flexible during congestion periods. Because of this, they are mostly used for personal and commercial purposes. Because of the urgent need to reduce greenhouse gas and other road transport emission and their adverse effect on the environment, this research is geared towards increasing sustainability and providing clean energy in the transport sector through the adoption of electric motorcycles. This research will contribute to the gap by quantifying the potential decrements in the greenhouse gas emission, which can be achieved by transitioning from gasoline-powered motorcycle to electric motorcycle. And this is a practical case study on the urban congested area in Thailand. This diagram shows the experimental design in Sumo, where we have the root file, the network file, the configuration file, the additional file, and the HBFA emission model is implemented in the root file, where we collect the output for the vehicle emission per time step and the absolute emission of the vehicles. Talking about the HBFA emission model and the emission standards, the HBFA is the basis used for calculating road traffic emissions, and this model has detailed emission factors for various pollutants emitted by different types of vehicles under the different traffic scenarios. This defines the emission factors for a wide range of vehicle classification for the fuel types, the technological standards used for the vehicles, and is especially notable for having the capacity to compute for the entire vehicle fleet, not just for an individual vehicle. The emission standards are a set of rules that govern and limit the pollutant emission for the vehicle to improve air quality. The standards are categorized for motorcycles Euro 1 up to Euro 5, while for the cars we have Euro 1 up to Euro 6, and the standards are continually being updated over time to be stricter, especially for carbon monoxide, hydrocarbon, particulate matter, and the nitrogen oxide. So this diagram shows the emission standards for the motorcycles, where we see the allowable limits for motorcycles following the Euro emission standards, while this diagram shows the allowable emissions for the cars. So why Sumo? Because Sumo is an open source, portable and microscopic traffic simulator, which is mainly used for handling mobilities in road network simulation. In previous work done by our team, Sumo has been calibrated with the actual traffic data measurements to emulate the real-life traffic situations of the Saturn road network area. And this allows us to be able to use the output directly to evaluate realistic greenhouse emissions. So this shows the overall simulated area of the Saturn road network area, where we have imputed the cars and the motorcycles. This shows the movement in the Sumo platform that was used in this research. We can see the vehicles moving as per the route set in the simulation file. This allows us to see that the vehicles indeed emulate the real-life situations where the motorcycles are able to move in between cars during the traffic period and come to the front of the stop line, just as we would have it in the real-life traffic situation. So this further validates our data to let us know that indeed it is emulating the real-life traffic scenario. So this table shows the parameter settings for the overall demand and network settings, while this shows for the vehicle attributes. We have the network settings for the whole network area and the vehicle attribute settings for each of the vehicles in the simulation, namely cars and motorcycles. Discussing the simulation results, this correlation matrix shows the relationship and interdependencies of the emissions with itself and with other emissions and fuel. Worthy of note is the fact that fuel as the common factor shows the linear relationship with carbon dioxide, particulate matter, and nitrogen oxide. That is to tell us that it has a linear relationship. The experimental result is shown in this table to let us know the limits and if each of the outputs gotten follows the emission standard that has been set for the cars and motorcycles. Experimental results. We can see the results shown for each of the emissions in this chart, where we have the Euro 3 emission from the gasoline-powered and cars for the baseline scenario during the traffic rush hour for an average of each of the vehicle. Here we see the emission of the cars and motorcycles against fuel to show the relationship for each of them. We have shown here that the emissions from the car, though they may seem higher than that of the motorcycle at first, but because of the larger number of motorcycles in the area, this makes the total from all the gasoline-powered motorcycle way higher than the total emission from the gasoline-powered in cars in the simulation. This further buttresses the point where we need to focus on motorcycles. This shows the electricity consumption of the motorcycles during the traffic morning rush hour. Lastly, the simulation results shows us that after the whole vehicles, that is motorcycles, have been transitioned to electric motorcycle, we have a 25.5% decrease in carbon dioxide, 11.8% decrease in the study suggests that carbon monoxide has been reduced by 25.5%, CO2 has been reduced by 11.8%, hydrocarbon by 54%, the particulate matter by 61%, and the nitrogen oxide by 43%. In conclusion, the study provides a comprehensive analysis of the potential for the greenhouse gas emission to be reduced if we indeed transition from the gasoline-powered motorcycle to electric motorcycle. The findings indicate that there is a significant reduction in emissions of the carbon monoxide, carbon dioxide, hydrocarbon, particulate matter, nitrogen oxide, and the fuel consumption. The transition not only supports environmental sustainability but also enhances urban mobility, thereby promoting urban health. Study implication and future research. We can use the results from this study to illustrate enormous environmental benefits of switching to electric motorcycle, but policymakers and urban planners should consider these findings when formulating solutions for sustainable urban transportation. There is going to be a reduction in hazardous emission, which can be of help to the cities, and future research will focus on widening the study scope to cover diverse geographic location, and the economic consequences of transition to electric motorcycles, including cost-benefit evaluation and influences on the energy infrastructure, could also be worked upon. This is our research team. Thank you for listening.